Hi guys. So this is going to be a more technical video on the background of Frobenius theory that's going to provide more formal proofs and the methods that are behind what we did in the previous section and that support the ideas that we're going to look at chapter 11.5. So we started with this differential equation, x squared y prime prime plus xp of xy prime plus q of xy is equal to 0. And we sort of informally looked at the case that if you solve the equation r times r minus 1 plus p naught r plus q naught is equal to 0, and r1 and r2 were real, and r1 was not equal to r2, and r1 minus r2 is not an integer, then at least we asserted that there are solutions that look like y1 of x is equal to x to the r1 times the sum from 0 to infinity of some power series, and that the second solution has the same form, where you can find these things using recursion. You can find an expression for the a_n's and the b_n's using a recursive or recurrence relation. So the problem is that this is a lot of very specific stuff that we've assumed here, right? We've assumed they're real, they're not equal, and they don't differ by an integer. And that's a lot to assume. And we didn't really talk formally about where this theorem came from. We sort of indicated where this might come from by assuming that since p and q were analytic, that the equation near 0 ends up looking like the equation for the Cauchy-Euler form of the equation. What I want to do is I want to go through where the theorem actually comes from and try to extend it to all the rest of the cases, because we have all this other stuff to deal with, right? We have to deal with what if they're complex, and what if they're equal, and what if they do differ by an integer. And so that's sort of part of the broader approach to these questions in Frobenius theory. The upshot is that if we ask the question, can I deal with all the rest of these cases? The answer is affirmative, that we can do that. It's just going to require a little bit more work. So let's start by looking at where the Frobenius theorem comes from originally. Let's assume that we have the equation that we started with, x squared y double prime plus x p of x y prime plus q of x y is equal to 0. And let's assume that we have a regular singular point at x is equal to 0. And of course what that means is that p and q are analytic at 0 on some neighborhood that looks like minus r to r, okay, with a positive radius of convergence. We're going to write p of x is equal to the sum from n equals 0 to infinity of pn x to the n, and q of x is equal to the sum from n equals 0 to infinity of qn x to the n. For some coefficients pn and qn, it doesn't really matter what they are, we just need them symbolically. We're going to write down the guess that we have for the solution. So we've already know that we've guessed that the solution has the form x to the r sum from n equals 0 to infinity an x to the n, guarded by our intuition that we developed in the last chapter, which is that it locally looks like a Cauchy-Euler equation. We don't know what the r or the an's are. One reason to justify this, if you don't want to use the argument that this comes from a Cauchy-Euler equation, is that because we have a differential equation that is being multiplied by powers of x, it makes sense that the answers to the differential equation should also have some kind of powers of x involved, because the product rule says that when you take a derivative of x, the power comes down, you subtract 1 from the power. So powers of x have the property that when you take their derivatives, you get powers of x back again. And that's another argument for why powers of x should even be involved in this equation at all. So what I'm talking about here is this. That should be involved specifically because we've got these terms, x squared and x, and they have to interact with the functions that we're taking derivatives of somehow. So if they're going to interact with the solution y, it's possible that y might itself have powers of x involved. And then the reason that we assume there's a power series is because away from 0, because the differential equation is sort of analytic looking away from 0, the power series is going to describe what that function does when we're far away. Now I'm going to rewrite this as y is equal to the sum from n equals 0 to infinity of an x to the r plus n, which just means I'm taking the x to the r and I'm putting it inside. And because I'm going to be computing in the differential equation, I need expressions for the derivatives. So y prime is equal to the sum from n equals 0 to infinity, r plus n, a to the n, x to the r plus n minus 1. And the second derivative has the same structure, but we've taken two of them. So we pull the power down again, and we subtract another one from the existing power. So we're going to take the expressions for p and q, and we're going to take the expressions for y, y prime, and y double prime, and we're going to plug them all into the differential equation. So the equation we're plugging this into is x squared y double prime plus x p of x y single prime plus q of x y is equal to 0. And I want you to notice that the x squared here is going to jump into the second derivative, and it's going to turn this r plus n minus 2 back into an r plus n. Same thing with this x. This x is going to go in and hit this y single prime, and when I multiply it in, it's going to turn this r plus n minus 1 back into an x to the r plus n. So when we plug in, this gigantor equation is what we end up with. And the first thing to notice is that every one of these terms has an x to the r living inside of it. So I'd put them in to calculate the derivatives, but you'll notice that after I put the x squared and the x back in, the powers of all these match. And in particular, x to the n plus r is x to the n times x to the r. So one thing that you can do here is you could take an x to the r out of each one of the equations and get x to the r is equal to the sum from n equals 0 to infinity of all the rest of this stuff. So using the 0 property, either x to the r is equal to 0 or this huge power series looking thing is equal to 0. X to the r can't be 0 for all x because that's not the way exponentials work. So the only way that this could happen is if what is now an actual power series is equal to 0. So the reason that we did that we put the x to the r in to calculate the derivatives and then took it back out again, is that now I have a bona fide power series where these are all just x to the n's everywhere. And so I can use all the rules and manipulations for power series. The one thing I have to do before I start combining these things is now I've got products of power series. And so I'm going to have to deal with these products of power series using the formulas for taking the product of power series that we developed in earlier sections. And if you do that, if you replace this and this with the formula for a product of power series, what you end up with is this expression. So in this series, it's going to be the case that we're still going from 0 to infinity because that's where we're getting the term x to the n, but that we're going to have sums to do in the coefficients. And that's going to look like this. Now, if we take this all together and we combine it, then what we end up with is the following. Notice now that I have an x to the n right here, and I have these two things together are an x to the n, and these two things together are an x to the n. So I'm at the condition now where I can pull the series, or I can take the series and I can smash them all together. I can pull the x to the n out one side and the sum out the other. And when you do that, you get the single sum. Now this looks kind of a mess because you have this enormous pile of terms where everything is involving terms that happen in the future. So what do I mean by that? I mean, for each value of n, this sum gets larger and larger because more and more of the previous terms are involved. But you can still look at the recurrence relation by pulling this part right here out completely, because now we have an actual power series equal to 0, and so the coefficients must all be equal to 0. And that means that we get the recurrence relation where an must satisfy the equation r plus n times r plus n minus 1, an is equal to the sum plus the sum from k is equal to 0 to n, and that this holds for n is equal to 1, 2, 3, etc. So if we evaluate this recurrence relation when n is equal to 0, then what do you end up with? Well, that says r plus 0 times r plus 0 minus 1, a0, plus the sum from k is equal to 0 to 0, so one term there, p of 0 minus k times 0 plus r plus q0 minus k, ak, is equal to 0. But a sum from 0 to 0 of this just means plug in the number 0 and see what comes out. So we get r times r minus 1 a naught plus, well, replace all the k's with 0, and what you end up with is p naught times r plus q naught times a0 is equal to 0. And all of that is just to say that r times r minus 1 plus p naught r plus q naught times a naught is equal to 0. We make the assumption that a naught is not equal to 0, and so it must be the case that this is. But that's just the index equation. So it's a lot of work, but the index equation is not something we start with. It's something that we can actually derive by looking at the power series for all these things and then applying the product formulas. Okay, so the last thing that we can do is we can reorganize this. So this object right here, we can reorganize to make it easier to work with. One way of doing that is, you notice that in the last index here, when we put n into the series, we would get an an out here. So we're going to reduce this series by popping the an term out and combining it with this an term right here. And that's going to give us a different recurrence relation, or a different form of the same recurrence relation, which looks like the following. r plus n minus 1 plus p naught r plus n plus q naught an. And now we get the sum of all the previous terms. And we can go a little bit further and say that what's actually happening here is we can write the recurrence relation like usual, like this. And we're going to define a function fr. We can think of fr as being the equation that corresponds to the index equation from the Cauchy-Euler case. So fr is going to be equation r times r minus 1 plus p naught r plus q naught. So we're going to define this function fr, and what fr is going to represent is the n equals 0 case of this function right here. And we're going to have the property that fr plus n is just equal to all of this. So all of this stuff right here is f of r plus n. And the indicial equation is just solving the case when is fr equal to 0. That's what gave us the r1 and the r2 from the previous structure. So this is all the pieces that we need right now. So what do we actually have? We have this gigantic recurrence relation. We're going to be using these functions to determine what happens when the roots are distinct, or they overlap, or they're complex. These are the bits that we're going to use that help us determine what the coefficients an actually are. So now we're set up with all the pieces. The next part of this is just going to look at what the individual cases are.